Next, we will look into white box testing. This is also known as structural testing. The idea here is that we investigate the internal code structure with our test cases. Consider the program that you see on the screen. According to the definition, it will read in an integer value that is between 0 and 100. It will use this value to compute the sum of integers smaller than the value itself. For example, if the integer value is 1, it will compute the sum of 1 plus 0. If the integer value is 2, it will compute the sum of 1 plus 2, and if the integer value is 3, it will compute the sum 1 plus 2 plus 3, and so on. Now we start testing this program. A reasonable tester would look at the specification of this program and start to derive test cases from there. The specification says that the I value must be between 0 and 100. So for a first test case, one could try -1, that is just outside the acceptable input value. And we would find out that this program executes correctly. It will end up in the error branch, input value out of range. Next test case could be I equals 0. We would find out that this would also execute correctly by outputting 0. If we enter in I is 1, we find out it also works correctly, outputting 1. If we put in 2, the correct value is 3. If we put in 3, we find out that we come up still with the correct value, 6. If we try something in the middle of the range, 50, we still get the correct value. If we try the upper boundary, getting close to 100, we find that 99 produces correct result, 100 produces correct result, and then again when we go to 101, we find that the input value is out of range. So the program appears to be working correctly. However, had we used the white box testing techniques or structural testing techniques, we would have noticed that not all the code is covered. So we do not cover all the statements in this program. So this program might be a bit of a silly program, since inside the loop that sums up the values, we have this statement that if the input value is 10, then the sum is always 1. But had we used the code coverage metrics of our test, we would have noticed that we never execute this statement here. And we would have been able to come up with the correct test case to identify this failure. So therefore, inputting 10 would result in a failure as the sum is 1. So in white box testing, the purpose is try to cover every statement, branch or condition in the program to ensure that there are no defects in the program. Now let's introduce a concept of control flow graph that will help in understanding the different coverage measures. If we look into the first line of the program, we see that it reads the input value I. This corresponds to this first box here on the figure. The next line is the input value testing. So it tests whether the input value I is less than 0 or if it's greater than 100. This conditional branch, this if, is corresponds to this diamond branch here in the figure. We can see the same conditional testing in here. And what we will notice here is that if the value of this conditional testing is yes, we go to the error branch, which is this line of code here. If the value of this conditional is no, we go to the else branch. So in this line, we set the value of sum to be 0 and x also to be 0. It corresponds to this box here. Next, we go into the while loop. So as long as x is less than the input value I, now this corresponds to this diamond shape here. If this condition is not satisfied, we jump to printing out the sum value. If this condition, however, is satisfied, so x is less than the I, we increase the value of x by adding 1 to it, which corresponds to this line over here. Next, we come to the faulty part of the program that tests if I is different than 10, and only if it's different than 10, it sums up, it increases the sum by adding x to the sum value. And this if branch is this diamond shape here, and only if it's yes, the sum is increased. If it's no, then it's omitted and the loop is executed again. So in control flow graph, statements that do not test any conditional, that do not have any branches, are represented by these boxes here. For example, read here, the error output here, the setting of the sum and the x values here. Then conditional branches, if else, are represented by these diamonds, and we can always see 2 arrows leading from them. Or they could be multiple if it's if, else, if, and so on. We can also see that the loops are represented by conditional testing first, and then returning back to testing whether this while value still works. So now you should understand the basic concepts of the control flow graph. Okay, now we can define some coverage measures. So the statement coverage is defined as the percentage of executable statements exercised by the test suite. So in other words, the total number of statements exercised divided by the total number of statements there is in the entire program. Let's have a look at an example program. This program has 7 statements. I will now point them with my mouse. So it has, this is the first statement, second, third, fourth, fifth, sixth, and the 7th. So there are 7 statements. 3 of them are branching statements, and 4 others are just regular statements. Now, let's consider a test case that simply flows through the program from top to bottom. So it would execute the boxes and the diamonds with the bolded edges. So first it executes this one, this one, this one, this one, this one, this one. So it executes the 6 statements that are on the direct path here from top to bottom. It doesn't exercise this statement here. So this program would have a statement coverage of 85.7%, which is 6 divided by 7. So it has been claimed that the typical ad hoc testing achieves something between 60 to 75% statement coverage. In our example program, it should be quite easy to reach 100%, as with only single test case we are able to come up with 85, and there is only this one statement we additionally need to cover. Whether it's possible to reach 100% statement coverage in the real world obviously depends on the program. If a program has a lot of dead code, it is obviously not possible to reach 100% statement coverage. However, then one should consider removing the dead code. Also, sometimes error handling code can be difficult to reach in normal testing scenarios. For example, assume that you have code on some hardware errors. For example, that you have a malfunctioning hard drive and you have some error handling code to take care of that. It would be quite difficult to come up with test cases that simulate the malfunctioning hard drive. Obviously, you could do it easily with real hardware by just unplugging it, but this would be quite difficult for automated testing. You would probably need some type of simulator to do that. And there could be other code that is just hard to reach. Let's have a look at the next coverage metric, which is called the decision, or also known as the branch coverage. So this is the percentage of decision outcomes exercised by a test suite. So number of decision outcomes exercised by test divided by the total number of decision outcomes. The program on the screen has 6 branches or 6 decision outcomes. I will point them and count them on the screen so that you can see. So 1, 2, 3, 4, 5, and 6. If we continue with the previous example or the previous test case that simply flows from top to bottom, we can notice that the coverage of this test case only has 50% branch or decision coverage. We have 6 branches and it executes 1, 2, and 3 of these. It doesn't go into this branch. It also doesn't connect back from this loop, and it doesn't exercise this branch as well. So we now have a second measure of our test coverage. First we had the statement coverage, which was 85.7. Now we realize that our branch coverage is only 50%. Obviously this means that statement and branch coverage are different things. We could also call branch coverage stronger than the statement coverage, as it is more difficult to reach the 100% of branch coverage than it is for statement coverage. It is claimed that typical ad hoc testing achieves between 40 to 60% of branch coverage. Here is another example of differences between statement and branch coverage. So we have the control flow graph we previously introduced. We have 2 test cases, I is -1 and I is 1. We can see that this results in 100% statement coverage. So I -1 comes here, executes the error branch, and the program terminates. Then I equals 1 goes to the no branch, goes the loop 1 time around, then in the next round the evaluation fails and the sum is printed and the program terminates. So we have 100% of statement coverage. However, branch coverage is only 5 out of 6. So we execute this branch 1, this branch 2, this is executed 3, this is executed 4, this is executed 5. But the no part, I equaling 10, is not executed at all. So we have 83% branch coverage. There exist more code coverage measures. So we have a measure called condition coverage, which investigates the internal structure of the control predicates, so that both true and false values of each predicate is taken into account. So consider an example of a conditional statement A less than 0, B or B greater than 0. If we want to achieve 100% condition coverage, we must ensure that both A and B part of this condition are tested for both true and false value. This can be achieved with two test cases, so that in the first test case A evaluates true and B evaluates false, and in the second test case A evaluates false and B evaluates true. Another two test set condition that satisfies the 100% condition coverage would be having A evaluate true and also B evaluate true, and then in the second test case A evaluate false and B be evaluated as false as well. Even more stronger coverage measures have been proposed. The next one is known as modified condition decision coverage. So it is basically condition coverage, but in addition, each condition is shown to independently affect the decision outcome by varying that condition only. And this condition independently affects the decision when you flip the condition and hold everything else constant. So considering the code example where A is less than 0 and B is greater than 0, we would need 3 test cases to satisfy 100% modified condition decision coverage. We would need false-false test case that would evaluate the false. We would need false-true, where it is shown that the evaluation of B to true results in this entire statement being evaluated as true. So it is independently so that the B affects the decision. And then we also do true-false, where we show that A, changing A from true to false, independently affects this decision. This modified condition decision coverage has been proposed by software industry. It was proposed by Boeing, and it is required in certain parts of aviation software according to their standards. Okay, so the final measure is called multi-condition coverage. As far as I know, there are no fields in the software industry that would require this level of coverage. So for practical purposes, one would stop at the modified condition decision coverage, because this is required in aviation field. But just to be complete, this is the most advanced control flow testing strategy. It tests each sub-predicate combination separately. So you execute all the sub-predicate Boolean value combinations. So for this A less than 0, B greater than 0 example, we would need 4 test cases. So we would need to test each predicate as separate, but also their combinations. So we need false, false, true, false, false, true, and true, true. Okay, here is another example. So considering a Boolean statement, if A less than 10, if B greater than 250, we get 100% statement coverage if we execute this if statement with any input. We get 100% decision coverage, also known as branch coverage, if the decision from this branch is executed for both true and false. We get 100% condition coverage if the predicates are individually evaluated as false and true. So we need 2 test cases. The first one is false and true, and the second one is true and false. However, this condition coverage does not require decision coverage, as the other decision, the true part, is never executed. The first one evaluates, the first statement evaluates completely as false because A is greater than 10. So the entire statement is false because of this AND statement here. And in the second one, the part B is false, so therefore the entire statement is false. So the next one is condition decision coverage. So in this case, we require that the individual predicates are evaluated to true and false, but also that the decision at the same time is evaluated to true and false. So we would need two test cases. First one would be both are true, and the branch or decision taken is then true, and then the next both are false to satisfy the condition coverage, but to satisfy the decision coverage, then also this becomes false. In modified condition decision coverage, we require that each predicate is shown independently to affect the decision, so we need three test cases. In first one, they are both true, and the entire statement evaluates as true. In the second one, A is false, so the entire statement evaluates as false, and in the third one, the B part is false, so the entire statement evaluates as false. And to jump from the modified condition decision coverage to multi-condition, we only need to add one more test case. This is so that they are both A and B are false at the same time. Now we introduce the concept of coverage strength. So the coverages at the bottom are weaker than the ones that are on the top. So if we start from the bottom, perhaps the weakest form of coverage that would have any relevance to software testing would be class or file coverage, which would be satisfied when there is at least one test for each class or each file or each module. It depends on bit on the programming language itself, whether it's class or file or module, or what is the level that we should be looking at. Slightly better coverage would be when you have method or function coverage. So it would be satisfied when there is at least one test for each method in the program. More advanced coverage again would be statement coverage, which would imply whether all lines of code are tested or what is the percentage of lines in the source code that are tested. Notice that in the figure, condition branch is not claimed to be stronger than statement coverage, because we can have condition coverage that is 100%, that exercises the individual predicates, but it may not execute all the statements because some booleans would be evaluated as a whole to false, and some statement might not then be executed. However, it is true that the decision coverage is stronger than the statement coverage. In decision coverage, all the different paths or all the different branches are taken in the program. A slightly stronger coverage would be condition decision, that requires not only that all decisions are taken, but also that all the conditions are exercised. Then even a stronger coverage would be the modified condition decision coverage, which requires that all individual predicates are shown to individually affect the decision. And then finally we have the multi-condition, where all the predicates need to be evaluated to both true and false. Without good white box testing tool, analyzing control coverage in testing is pretty hopeless. So in the exercises you will be using the ECL EMMA tool, and it will highlight the quality of the testing you have done. We have red lines that means tests are missing. There are green lines indicating that it is covered by test. And then additionally there would be yellow lines, meaning that the line is partially covered. So what structural coverage can tell us? Well, it can clearly identify if we are missing some tests. Is there a need to do more testing? It can also indicate the need to have better tests. It can point out risky areas that are hard to cover by testing. So if you have areas where you reach only like 30% of statement coverage in testing, and it's difficult to go much higher than that, then it might be a good idea to do some type of other quality assurance like reviews. It can point out unreachable code, old code, dead code that perhaps should be removed. So it can also give an indication of the maintainability of the source code, but this is not its primary purpose. Finally, what can we assume if the coverage is high? Well, basically it tells us that our tests cover the code in terms of the used coverage criteria. The coverage criteria itself does not indicate whether our tests are good in detecting defects. So we might have high coverage, but if the tests have poor ability to detect defects, in other words, they have a poor oracle, then we might be happy with our high coverage without realizing that there are still defects in the software if the detection capabilities are low.